Hey, I'm Dave. Welcome to my shop. Today in Dave's Garage, we're going to continue our work on individually addressable RGB LED effects by starting with a single green ball. First, we'll make it fly. Then, we'll make it bounce. Once we get that working, we'll use what we learned writing the comment in our last episode to add a persistence effect to the ball's path. The faster it goes, the longer the trail. From there, we'll add support for multi-ball. I'll show you some very basic use of the C++ vector class to allow for any number of balls all at once. I'll also demonstrate how to do simple additive color blending with fast LED so that, for example, when a red and a blue ball cross paths, the result is automatically magenta. It's a one-line change if you know the right line to change. Next, we'll double our fun by simply mirroring the effect. I'll demonstrate how to tune and tweak all the parameters of the effect for the most visual impact. And as always, while I code live in the editor, you see the actual results immediately right down here. This effect is very flexible, and in fact, it's what's running on the atomic desk lamp here behind me. Everything we learn here will lead directly to our next lessons, when we tackle fire, flame, and then the particle system needed for shooting stars and fireworks. But that won't make any sense unless you see this first. So grab a coffee and settle on in while I show you how to build a bouncing ball effect that really goes to 11. It's time to add another layer of defensive coating to our fast LED code so that we don't smoke our USB port by drawing too many white pixels or just drawing too much power in general. Most good controllers will go whoa and shut you down, but who knows? I don't want to risk it, so there is functionality in fast LED that can help protect you, and it's time to introduce that. So let me do that real quick. Let's head into the editor and we'll take a look at the normal source file that we start with every episode. This Hello World example really just sets up the LEDs, sets up the little OLED display that we're using, and then calls draw repeatedly. But that way, I'm not complicating your life with a bunch of class libraries. I just hate it when people are trying to teach you something and they're like, here, learn my class library. No, I want to learn the actual thing, not your class library. Although in this case, we are learning fast LED, but that's because it's like amazing and will, save us tons of work. It's also really an API and not a class library, but hey. Let's head down to the setup section where we set up the LEDs. Right here, after the set brightness call, I'm going to introduce a new function that sets the maximum power in milliwatts that we are willing to draw. We'll take a more in-depth look at this functionality in a future episode, but for now, just know that if we ask it to draw too much, let's say we just filled the thing with white and let it draw. Normally, that would take something like 9,000 milliwatts if you had about 50 LEDs. And this will say, no, we'll just cut that back by a factor of about 90% and draw everything at about 10% brightness so you get all the LEDs you asked for, but you get them at a much more dimmed appearance. So it protects you by not drawing too much power, but still shows you what's going on. The next thing I'd like to do is where we're printing the stats information about frames per second, I want to print out the number of milliwatts we're pulling at the same time. Actually, no, I want to know the number that we're requesting. I know it'll never exceed the 900, but I want to know, what did I actually ask for? So to test this, I'm going to ramp everything up to full bright white at a brightness of 255. If you're doing this, make sure that you either have a massive power supply and not your USB bus running it, or that you put the power limitation on in the code that we just added a moment ago. Okay, let me upload it, and I'm ready to unplug it. We'll see what happens. It's going to start it all black, and then when it flashes and turns on, it's going to turn all white. Here we go. So as I suspected, about 9,600 milliwatts or 9 full watts of power. That's a fair bit to ask of your USB bus, so fortunately we've limited it to 1/10 of that, which means everything's going to be scaled back in brightness by about 90%. I think the calculation is a little smarter than that. It even takes into account the different power loads required for green versus red versus blue and so on. However, it's not perfectly accurate. But it seems happy, and I have not had a PC or a Mac complain that the power load is too high as long as I've kept it under 900. So your mileage may vary. I'm not a hardware guy, but hopefully that works for you too. Well, with that out of the way, our normal procedure is now we're going to create a header file, we're going to save it, we're going to fill in the information, we're going to put in the pound includes. Let me do that real quick. So two things are new here. The first is the inclusion of sys_time.h, which I need in order to be able to get the time in the number of seconds since 1970, which I'm going to use to create a floating point time, which will make it easier to multiply than having to do milliseconds and multiplying by 1,000 milliseconds per second and fancy math like that. I'm just going to do it for the sake of simplicity, all in floating point math. And rest assured, the ESP32 does in fact have a math coprocessor built in and floating point instructions and so on. Whether the native type is float or double, I don't actually know, but hey, I should look that up someday. The other thing you'll notice that's likely new to you here is the inclusion of vector and the use of the using namespace standard. What that means is I'm going to include the header file for the C++ variable sized array because I'm going to allow you to specify how many bouncing balls you'd like to have. The caller can specify that, and so I need to allocate them dynamically. Instead of doing a bunch of mallocs and stuff like that, we're just going to use a variable array, and we're going to make pretty simple use of it, so don't freak out. Wait till you see it. It's not very scary. Using namespace std just means that you can assume I'm always in the std namespace, and that if you can't find it, look in the std namespace, because vector is in the std namespace. If you didn't say using namespace std, you would have to specify std : vector every time you referred to the type. I don't want to do that. That's what that's for. I'm going to define a helper function here that allows you to measure the number of array elements in a statically defined array. So if you have like a string, a bunch of a character array, for example, this will tell you how many array elements are in it. This works by dividing the total size of the array in memory by the size of an individual, in this case the first element. That tells you how many elements there are. The first thing I need is something like the twinkle effect. I just want a little table of simple colors that we can use for the bouncing balls. Because again, I don't want to randomly pick them, and even if you step through the color wheel, it doesn't look good at going red, orange, yellow, green. So I like to go red, green, blue, orange, violet, that kind of thing again. Those then are the 5 colors that we'll use for the balls. If you have more than 5 colors, it will just wrap around and the 6th ball will be again green. These are the basic attributes we need for the effect. The length of the strip, how many balls we're going to place in it, the fade rate that we're going to fade out the strip, because we're not going to just clear it, we're going to do like the comet effect. The mirrored flag is whether we're going to draw the ball strictly bouncing from one side or if we're going to draw 2 balls, one from each side, so that we get sort of a balanced effect. So the gravity variable is something we need for kinematics in order to calculate the position of the ball. It turns out to be a very simple formula, as in a single line, and you'll see it coming up in a moment. Start height is a floating point variable from 0 to 1 of the height of the ball. We're going to drop the ball from the max height of 1 to get it started each time. If it's perfectly elastic with no dampening, it will return to 1, but if it has some dampening on it on each bounce, it will get smaller and smaller and smaller. That's my idea anyway. Impact velocity calls a function that I haven't yet written in order to calculate what the speed of the ball is based on its height. That too is a simple calculation, and it's one I'll add in a moment. Speed knobs, it's a speed scaler. If you move it up and down, it changes the speed of how fast the ball ramps back and forth. These are the fancy C++ arrays that will contain the information about each of the balls. For physics, each ball keeps track of the time that it last impacted the ground, its height, the current ball speed, and the dampening factor for this ball, which is basically how bouncy it is. We also need a little array to contain which color each ball is. So far, everything that we've written here is private and internal to this class. That means nobody else is going to call this code directly, so I'm going to protect it by marking it private, and then it's not even visible outside of the C++ class. In C++, you can and should mark any function that doesn't change the state of the object at all as a const function. And that tells the compiler it can make some assumptions, and it makes things more optimal and faster. Ideally, anyway. So that's our signature. That's what you have to specify when you instantiate or create a bouncing ball effect. The number of balls, the number of pixels on the strip, the rate at which it fades out, and whether the effect is going to be mirrored or not. We'll then use that information passed into the constructor to set up all of our arrays and member variables. One thing you might find a little odd, and it's kind of a hack here, is that I'm going to actually only use all but one of the LEDs in my length calculations, or in any of my calculations. And then I'm going to overdraw by making my little ball 2 pixels wide. And that's just to make it more visible. There are probably more elegant ways to do it, but I'm trying to keep things brief as well. These 5 arrays, the clock time at last bounce, the dampening, the height, the ball speed, and so on, are arrays that describe each of the balls. We need one for each ball, and so here we're able to specify how big those arrays should be, and of course it makes sense that they are ball count size. Unlike C, where you can only do that at compile time, in C++ you can pass that to the constructor of a vector, which is basically the dynamic array. Now we'll initialize the arrays with the information needed to represent each of the balls. By way of explanation, height is pretty self-explanatory. All balls start at a height of 1. We're going to drop, no matter how many you drop, and we're either really going to initially drop 1 or 3. We'll start with 1, but when we go to 3 balls, they'll all fall as a unit until they hit the first time, and then their different springinesses will cause them to bounce differently. But the dampening isn't taken into account in this initial launch, and that's intentional, so that they all launch together and then come back down and then bounce and separate, which you will see when we get to that point in the effect. But I want to explain what's going on with that code right here. Clock time at last bounce obviously keeps track of when the ball last impacted the ground. We'll call that the start time to get going, and from there, every time the ball impacts, we'll set it. Dampening is a function of how springy this ball particularly is. And so the closer to 1, the more energy it preserves on each bounce. And the reason I even keep track of this is that we have multiple balls, and it allows them to bounce differently and separate, because otherwise they would all just bounce as a unit. So by having them all be a little bit different, they bounce at different rates, and things look a little more visually interesting. Ball speed is actually going to be the same for them all, even though it's calculated, because they're all starting out at 1. And colors is an entry into the color table, but it wraps around. The ball index is modulus with the size of the array. So if we have 5 colors in the array, but we're on the 8th ball, we'll be wrapping around back to the 3rd color again in the array. It only matters if you have more than 5. So this initial portion of the draw code is responsible for fading or clearing the strip depending on whether or not we've set a fade rate. If the fade rate is set to 0, we take that to mean clear the strip each time, not fade by nothing each time. So the least you can fade by is 1/256th. Here we assign to time since last bounce a number which represents the amount of time that has elapsed since the last bounce. If we use the raw number of seconds, however, it will be a little fast. So for a display this small, I'm going to divide by a speed knob, basically a 4, which is just a number I picked because it looks good on my small strip. But if you're using even a full meter or 2 meters or something like that, you may not need this at all, and you could use the raw number of seconds. In any event, it's a parameter that you can tune to make yours look the best it can, or look like you want it to, more or less. So obviously when height goes to 0 or below 0 at least, that's when it indicates to us that the ball is bouncing and needs to be reflected back up the other way. All we're going to do is we're going to set the ball height back to 0. We're going to set the ball speed to max as if we're dropped from the maximum height and fire it in the other direction. In this case, position is just calculated as a ratio, 0 to 1, of the entire strip length. For example, so I'm going to draw 2 pixels back to back just to make the ball. I could just draw 1 pixel, but it moves so fast sometimes that the trail that it leaves behind would actually have gaps in it. So unless you're going to do a line draw in here, everywhere that the comet or ball has been, you'd like to fill with pixels. So you really want to do a line here. But since we're just doing a single dot for simplicity, that dot has to be a little bigger just to cover more of space. Now, if it's mirrored, we're going to draw not only from the left, but we're going to draw from the right as well. And I'm going to shoot for around 50 frames a second, so we're going to delay 20 milliseconds. So now that our effect looks like it should be able to draw something, we need to go back into main and do 2 things. First of all, we have to declare an instance of the actual ball effect, because we can't just call ball draw, because we actually have to call it on the effect. We're going to declare an instance of the effect class as an object, and then we're going to call draw on that. We'll start with small ambitions, just 1 ball. There's a Hitler joke in there somewhere, but I'm not going there. That should be all it takes. Let's build it and find out. Let's take this line out. Rather embarrassing. All right, cool. We got a green ball bouncing from left to right as we kind of wanted. And when it settles, it should kick back up and start over. Now that we have that single ball drawing properly, let's go and add persistence to it so that we get that trail behind it as it moves. If we refer back to the drawing code, If we give it a non-zero fade rate, it will apply that fade rate to every pixel once per pass. So if we pass 32, it will fade every pixel by 32 out of 256 each and every pass. That's a good place to start, so let's try 32. Actually, let's try 64. I remember last time I think we started with 32 and it was too low, so I'm going to try 64. The faster it goes, the longer the tail is, and it really gives you a sense of smoother motion than just the individual LEDs being drawn, I think. Now let's launch multiple balls at once. We'll try 3 and we'll see how it looks. There's one thing I want to point out to you carefully in the draw code because it's not obvious from just first glance. That is that the ball speed, when calculated on a bounce, includes a dampening factor, so that each ball bounces slightly differently, and that way they stay a little bit separated. So I can launch all 3 at once, they can come down as a unit, and when they bounce, they kind of spray apart. But on the initial kick, I don't want to apply the bounce factor to it, I just want them all to go at the same speed. You'll see what I mean once you see the animation launch, but that's why up in the constructor, we actually set it slightly differently. We don't apply the dampening factor. Don't worry about this too much, but if you're wondering why all 3 balls stick together to make the first launch and then they break on the first bounce, that's exactly why. So here, ball speed is calculated strictly based on the height, but here, ball speed is calculated including the dampening factor. All right, 3 balls, take 1. I'm going to make one change to this before we launch it with all 3 balls because it won't draw right in my mind otherwise. If we draw all 3 balls, and we just draw them in order, 1, 2, 3, red, green, blue, whatever order they're in, the last one to be drawn is the one that you'll see. I don't really want that. I want the colors to blend. If the blue and the green balls overlap, for example, I want them to appear cyan as they pass across one another. To do that, we're going to make the colors additive, and we're going to use the plus equals operator, which is the same as saying, take the LED and add this amount to it. It is clamped at 255, 255, 255, so it won't overflow. It will just lock itself on white. So let me make that really simple change to the code now. Then we'll launch all 3 balls and see how it looks. This is all that's required. We'll upload it and we'll know it works if the ball draws as white when it launches. And indeed, you get a single white ball, which leaves a trail that's mostly white, but you can see some hints of the individual colors. And when it impacts, splits into all 3 colored balls individually. Now, the next most easiest, cheapest, and simplest thing to do that's going to give us the most bang for the buck is to mirror this effect. So let's just turn on the mirroring that we already added in the draw code and see how that looks. So our effect's going to be running with 3 balls, a fade factor of 64, and it's going to be mirrored this time. What else can we do to turn this one up to 11? Well, we can add more balls. It never hurts. We can also turn down the fade factor a little bit here. I need to correct one thing here. My initial typing of this had the delay inside this for loop. We need it to be outside the for loop, but inside the draw. So let's make sure that's the case. Otherwise, I noticed as I started to add more balls, I got more delay, and that's not right. It got slower, and I'm like, can't be that hard to draw a pixel, can it? And indeed it is not. But, all right, I think you can see there's a lot of legs in this particular effect. You could take it and modify it quite a bit further, and I encourage you to do so. Tinker with it, play with it, change things around, especially with that power cap in place. You really can't do any harm, so have at it. Have fun, and if you come up with a cool variant, let me know what the code change is in the comments, and I'll share it with everybody else. I hope you like the effect, and I hope it serves as a basis for a lot of cool experimentation for you. As always, I'm not selling anything, and I don't have any Patreons. I'm really just in it for the subs and likes. So don't leave me hanging. Please be sure to leave me at least one of each before you go. Join me next time for a little pyromania as we take on a realistic fire flame effect. From there, it's onto a simple particle system for moving stars and fireworks. So if you're not already subscribed, please be sure to do so, as this channel is so small you'd otherwise certainly miss it. In fact, you'll likely need to turn on the bell and personal notifications as well. That way you'll actually get a notification about new effect episodes. Thanks for joining me, and I'll see you next time out here in Dave's Garage. That way, no matter how many balls you have, it can actually... That way, no matter how many balls you have, you can always find. Put more simply, perhaps, ball colors just wraps around so that no matter how many balls you actually have in the index table of...